and some of them include several papers by other people. And I will first start with reviewing the rather old work from 2020. It was a group of people that were trying to connect the language models of that old time, 4 years ago, with whatever can be recorded from human brain. And at first in the 2 papers that appeared in 2020. So these are archive versions. If you search through the names, you will find these things easily. And so they first explained that the inspiration was from the study of deep convolutional neural networks, which are used for recognition of images. And so their architecture was intended to imitate whatever living brain has. And so they mentioned the ventral stream. Ventral stream is just a part of the processing pipeline that the brain uses when you're trying to recognize what you're looking at. So they basically did an overview of different papers, and they say that if you compare different types of networks, you see correlation between 3 different things. So first of all, you could look at how accurate this network is recognizing objects. So accuracy of the core object recognition task. Then you could ask it, fine, can you predict how accurate would a human be at that job? And so this is number 2. And then number 3 is the hardest to actually implement. You try to record signals in IT cortex, and IT is inferior temporal, so this is somewhere here, not very far from the eyes, but like on the other side of the skull, obviously. And if you try to look at how the signals behave, then you can ask your network to try to predict that behavior. And it turned out that all 3 performances were correlated. So if a network is very good at recognizing images, it's actually very good for some reason at predicting how the human brain signals will behave, which is a little surprising because on one hand, yes, we created these networks to imitate the living brain, but then eventually people had to depart. Like you cannot really reproduce a living brain hardware, and it doesn't make sense even. Although there were some attempts maybe a year ago in France to create chips which imitate neurons more precisely. But basically, you're running algorithms which are inspired by the human brain, but they're not like equal to what you would expect. And for some reason, if they're very good at doing the job, then they're also good at predicting what the brain does. So they tried to implement this not in the area of convolutional neural network, but the language models. And so they have found something very, very similar. So they took a few models, whatever was available back in 2020, and that included, the top of the line was GPT-2. And of course, their issue was you have to use the model where you have access to weights. So it needs to be reasonably publicly accessible. So what they did, they recorded some information from the brain in 3 different ways. And so this will be discussed. So there are two sources of this information. So the easiest source, the one that's not used, would have been what is called EEG encephalography. But you do that by recording things on top of a skull, and skull will produce a lot of noise, and so the data is not very reliable. So there is a method, fMRI, where you look at the brain and you detect the blood flow in different regions. And so as brain is working, it will call on more resources and the blood flow will increase. So you know which regions kind of light up and which dim down. And so depending on this blood activity, you're inferring, okay, so something is active here. And it can be fairly high resolution. You could track the blood flow related to a very small region. There is also a version of EEG, or Koji, I think that's how we say it, where if for some reason people need to have brain surgery, or if they maybe have epileptic seizures and the medicine doesn't work, sometimes you need to open the skull, or maybe open the skull and implant electrodes. So this is obviously a very rare situation. There are not that many people, and not that many people would actually agree to participate in experiment. You can just imagine that, you know, someone opened your skull and just, why don't we do some fun experiment for 30 minutes and then we'll cover it up back. Right. So this is, the people don't have a lot of data, and all the available databases are very precious. And one effect that they're explaining here is that when you record the data, you're not even expecting that 100% of that data should be computable. You're expecting that a lot of this data is noise, or maybe some of this data is not relevant to specifically language processing task, because the same brain is doing a lot of other things. And maybe you're just hearing signals from a nearby brain region, which is involved in completely different situation. So basically, they say that they're trying to predict the useful part of the signal. And so here's the output, that if you only look at the estimated useful part of the signals, the best models, it can explain pretty much 100% of that explained variance, or the change of the signal, again, up to noise ceiling. So you assume that only part of that signal is useful. And they say, okay, the earlier generations account up to 30 or 50%, which is not that bad at all, but you see a very serious difference. And so then they notice that when they're trying to study such a question, which metrics could you say the brain is using? So how do you correlate performance of a AI model and the brain? And they realize that they can see correlation between three things. Neural fit. Neural fit is how well the algorithm would predict brain activity. And then a second performance would be reading time. So you give someone a text and they ask them to do self-paced reading. And it's viewed as one of the measures, how long does it take to read that text? Because if you're running into a word which is unexpected, then your brain needs time to process it. And if you're reading without forcing yourself, so this overall reading time will kind of reflect how surprising the next word is for the living brain. Okay, and then a completely abstract measure not involving a human. So you could, if you're given a text to the model, is it accurate in predicting the next word? Okay, so the amazing thing is that you could take other measures of linguistic performance, but no other linguistic task was predictive of models fit to neural and behavioral data. So you could try to measure human performance in different ways, and then you could try to evaluate performance of the abstract model. And so these correlations just fall apart. So their interpretation is that it's probably an indication that we have inside an algorithm which is also trying to predict the next word. As we're listening to a text, we are also solving the predictive problem. And in which way, so that remains to be discovered. Basically, the difficulty is that our imaging methods are not perfect at all, right? So we're either looking at the blood flow, or we're tapping into actual electric signals, but in random places, whichever was convenient for other reasons to have electrodes. Okay, so their conclusion is that the brain's language system is optimized to extract meaning through predictive processing, so predicting the next thing, right? So everything that's written on the screen here, you could read along, but so this is copied from these papers and sometimes in a shorter version, and I will just try to emphasize just whatever is highlighted in boldface. Another thing that they realize is that it is really a big deal which network architecture you're choosing, because you could have some primitive architecture, but hope to slam a lot of parameters, and you decide, okay, maybe you can win by numbers, and the answer is no, not really. So your training doesn't help, and if the architecture doesn't match some successful patterns, then you will not have good correlation. Okay, another thing, okay, so they were working with different data sets. So first, they looked this fMRI imaging, the blood flow imaging for, while participants read short passages, and they were presented one sentence at a time. And then these electrodes, but open brain electrodes, when they were reading different sentences, again, presented one word at a time. And then similar blood flow, but looking at specific regions that were active across a 5-minute short story. And just running ahead, this will probably give the worst correlation. And maybe because when you have a long story, people are trying to track a really long context and decipher implied messages, and maybe this is what the models are not doing yet, at least not 4 years ago, not to the same degree. And then in this specific study, they decided, okay, let's extract those responses that come from the brain regions or brain cells that we know to be related to language processing. So this is kind of a big deal, because sometimes you don't know quite what you're listening to. Okay, and so they used some kind of localizer algorithm, and that was identifying of what they call frontotemporal language selective network, which means just a bunch of brain structures which are involved in language. And the way they were selecting this, they were contrasting sentences with responses to non-word sequences. You can just blabber random sounds, and that in that case, the audio system of the brain is also participating, but maybe language isn't, just because there is nothing to recognize. Okay, so now what did they do exactly, right? So I'm trying to comment on just a short piece of this. We fit a linear regression from, and the big deal is linear, and I will say again why. From the model activations to the corresponding human measurements, modeling the response of each voxel or electrode region as a linear weighted sum of responses from different units of a model. Okay, so what does it mean? It means that they're taking a model, and then there's maybe some hidden layers, which we know are just matrices and numbers in these matrices. And we say, if we know the outputs, not just at the final stage, but if we know what happens in these hidden layers, we have different bunches of numbers. Can we find an appropriate linear combination of these bunches of numbers that will match the level of activity in a brain cell or in a brain region? So the big deal is linearity. Can we find a linear transformation that maps numbers involved in AI model onto the numbers that you're observing in a living brain? Okay. And so then again, they emphasize that they're only trying to look at the useful part of the brain signal. And Okay, so here are the
Sorry, can we ask a
outputs.
question?
Yes.
So to make sure I'm understanding, they're like you've trained some neural network model on some task, and then you're like comparing the brain performing the same task and trying to create a link map between like the weights and biases of the neural network that's been trained. And what exactly are we mapping to in the like brain setting? Like where are the parameters?
So in the brain setting, we're recording activity of particular brain regions, or you could say brain cells, and this is what they mean by voxels. So they if in the case when you have electrodes, a human could have a bunch of implanted electrodes, in some cases dozens of them, and then you could look at the signal that a particular electrode is sending, and you need to process that signal, and so there will be some mention of that. But basically, the raw numbers that you get from the brain, they do mention that they apply. I don't know, maybe not in the next paper. Maybe they apply a logarithm and normalize, but that's, I think, it's a standard practice in this business. Right.
But I guess like theoretically the like brain signal would be like the post-activated neuron or node value like within a neural network. Is that what we're like? Okay.
Well, whatever your imaging system gives you, because fMRI gives you an estimate of blood flow. You see intensity of blood flow in a particular region, and you estimate it by a number, and you say, is this number a linear combination of what the artificial algorithm is seeing. And of course, you need to train, you kind of need to train on the coefficients of that linear combination. But basically, the report is that, so the better models, and so, yeah, it's completely unreadable. In the left diagram, there is 43 models used, and the ones on the left are the things like word-to-vec embeddings, like these easier models which do not try to detect context of the word. And on the right-hand side, so they're using GPT, and GPT is number 2 because this is from 4 years ago. And they tried to estimate eventually how much of that useful part of the signal can be predicted by different models. And they see that the better models get to 0.8 or even to 100% of the useful part of the signal. And so I want to emphasize here that the useful part of the signal is estimated in 3 different experiments as 0.32 of the total size, or 0.17 or 0.2. So it's much less than a half of the living brain signal is considered the useful part that's predictable at all. So in their version, GPT-2 could get whatever they consider predictable. Okay. So this the best picture is the one on the left-hand side, the large one, and this was fMRI and sentences being read, and then in the middle, the 2 smaller pictures, the one on the top is cortical electrodes and still sentences being read, and then the one on the bottom is fMRI, but responses for long stories, like a 5-minute story, right? So it's very hard to decide why response to a 5-minute story has much worse prediction. Maybe because as you're listening to the current sentence in the story, maybe you're still digesting the previous sentences. Maybe there are some associations to that, and maybe your mind is busy with other stuff. But basically, you see that the numbers are much worse in this case. There is the right column of this where they compare a GLOVE model and GPT-2 model, and GLOVE model is, again, context independent, so the easier word embeddings, older model, which doesn't perform that well. But if you try to detect which regions of the brain they're responding to, so GLOVE has this corresponds to the first and the third picture of the brain where the color is red and your correlation is closer to 0. And then GPT is kind of, you could see it's aligned even with slightly different brain cells, and the correlation is close to 1. Okay. Right. So this is their estimation of different models, and so they try to just estimate what is it about the model that makes it good at predicting the brain behavior. And their ultimate decision is that models' ability to predict an upcoming word and ability to predict the brain behavior, so those things are very correlated. And so they were saying, okay, even within a specific model architecture, within specific algorithm architecture, you could have slightly different versions of your artificial neural network with same architecture, but maybe different parameters, maybe different procedures of training. And so in all of the cases, even when you fix the architecture and you choose slightly different models, again, those which will be better at predicting the next word will also be better at predicting what the brain does. Okay. And then they looked at what they call glue benchmark, and this is basically just a standardized benchmark about other linguistic grammatical measures of performance, grammaticality judgments, sentence similarity judgments, and so on. And so they found that all of these other features were irrelevant, actually. So their conclusion is that at least in the language area that they're studying, so the attempt to predict correctly what's coming up is most correlated with what the brain does. Again, the expectation that maybe it's not even language related, but everything else. If you're processing sounds or visual information, so it's natural to expect the same thing here. And also they realize, yes. Huh?
Is that assessment that the predicting the next word is like most correlated with brain behavior at all related?
Yes.
Is that related to the fact at all that a lot of these large language models are just like trained to predict the next word, and like that is what they're
yes, but if you're training them to predict the next word, you could still later evaluate them on other stuff. And if you train 10 slightly different networks with similar architecture, if you train them in a similar way by next word, but then you evaluate them on different, you rank them on different, in different other ways, then only ranking on prediction will agree with ranking on being brain compatible. So if you try to rank them on other performance, and this is what this glue benchmark is about, if you rank them on other stuff, then it's not true that the best grammar compatible model is the one is the best brain compatible model. So that's what they say.
Thanks.
Sure. Okay, so then they say that one thing that did come up with fairly good correlation is actually when you try to estimate how long does it take to read a particular sentence or paragraph. And here the correlation is worse, but when you're estimating the time to read, you don't need to do fMRI, you don't need to open anyone's skull. This is very, very available. And from reading other papers, I can estimate that also it's probably very helpful to look at the pupil dilation dynamics at the size of the pupil, because it's understood that it's estimating cognitive load, the amount of computation that the brain is doing at the moment. And also, it shows in our internal experience as subjective flow of time. So if we have high cognitive load, then it's one flow of time. If we are bored, then it's different. All right, so let me actually keep jumping around because, so I probably have more than I can discuss. And then they basically, so just emphasize again that some architectures are just so much better than other architectures that even when you don't train much, if you say, I'm taking my GPT with random weights, but I want to, but I do some training on how GPT weights, which of their linear combinations will predict my brain activity. And so even untrained GPT does pretty well. And obviously training of the AI weights improves things, but if it was bad to begin with, it will not improve by so much. So this is what they're saying here. Okay. Now the same group 4 years later, and this is a publication date, not exactly the same, but maybe I guess three people in the group are also authors in the earlier text, right? Hosseini, Shrimpf, and Fedorenko. So there is a publication of June of this year where they're discussing a different topic. So they say, if you look at the studies of these neural network models, they say the usual criticism is that their training data size surpasses the amount of language exposure in humans during their learning phase. So if you're training a model on billions of words, no child ever was exposed to billions of words. And then they went through literature, and then they say, okay, so the estimate is maybe that by age of 10, you're somewhere between 9 and 110 million words. And so the challenge was, if we train the model at this amount of words, how well would it do on predicting compatibility? How compatible will it stay with the human brain? And so they do it in two different ways. So in first way, they basically say that if you can train, expose the model to 1 million or 10 million or 100 million, 1 billion words, and maybe you're using many passes, but basically you kind of freeze the number of words that would be given during the training. Or you could start training it, and so maybe at first it's not exposed to a lot of words, and then you throw in more, and you can track how the model develops as you go. So this was their second approach. And also they used two slightly different sources for GPT-2 numbers. So for one was Deep Speed library, and the other is Hugging Face Transformations library. And I'm not an expert, I wouldn't even know where to download it. Okay, so maybe let me speed it up a little faster. Basically, what they're saying, I'll just discuss this picture only. What they're saying, if you care about, not about abstract performance of your language model, but its compatibility with the brain, then they basically find that exposing to too many words makes this brain compatibility worse. So they, in this experiment, in part A, that they have this little star at 100 million words. Like, this is very optimistic estimate of how many words a child was exposed to. But basically, this is where it will either level off afterwards, or in some cases it actually, I don't have that table here. They were trying to pull out different layers from the GPT model, And they said that for some layers, it actually gets worse as you expose it to more words. So by common standards, the GPT model is performing better, but its compatibility with the brain data gets worse. So if you want it to be compatible, then you need to know where you want to kind of stop with that. Okay, so let me maybe jump through this, and yeah. So let me just repeat what I said with different layers, just quoting them. So there is discussing performance across layers, consistent increase all layers up to 1% checkpoint. 1% of the words that maybe, what is it, 10 billion words that they will use. At 1%, up to 1% improves. Then you say that early and middle layers of the GPT model actually drop in performance after you expose them to 10% of the words. And then later layers of the model, they still keep getting better up to 100%. And then if you try to go 10 times 100%, just way too many words, unrealistically, then their compatibility with the human brain reaches a plateau, doesn't get any better. Okay, so this is the short addition to the earlier project on overlapping team, and that's a very recent study. So another, the second project is published in Nature Communications, I guess last week. And so they're doing something similar, except they kind of got hold of the data of 3 epileptic patients which had electrodes implanted in a specific area. And so they were working with the data from that area. And so this is anterior frontal gyrus. So what I like about this study is that try to extract which common features one would expect to hold both for the brain and for the algorithms in terms of kind of successful compatibility. How do you work with on the brain side? Which models do you select on the AI side? And the first thing is obvious by now. So you embed words in a continuous vector space and disregard the word continuous just in a vector space. So words are vectors of numbers. They're not discrete labels. They're not discrete structures. So then they say use self-supervised neural networks to embed the statistical structure of natural language. What they mean, don't use any handcrafted or pre-cooked data sets. And number 3 is also very important, that you want to work with AI models which contextualize the embedding space. So if you're saying that meaning of the word is encoded by a vector, then this vector should depend on the current context. So this vector should be sliding if you're changing the context. Okay, right. So they first they explain that they're using a specific area, high language level language area, IFG. I would criticize a little bit the word they're using with demonstrate, but there is very strong evidence that if you listen to that specific area, then you will hear some of the data related to language processing and in a format that is similar to algorithms. Okay, so then they do again, linear approximation. So they say we have something coming from a model and we have something coming from the brain, and let's apply a linear transformation on the AI side. Let's try to match this to what the brain does and see how well we can do that. Okay, so this is where they mention zero-shot mapping strategy. Right. So what do they do? So first they describe the data they have on the patient side. So they have three persons, and the number of electrodes is 41, 14, 26 respectively. So they have a total of 81 cranial electrodes in the area that they need to study. So they only have 81 data points that they kind of bundle together. So their embedding vector has dimension 81. And they are looking at the electrical signal there, and they're listening to different frequencies. So you kind of try to expand it in a Fourier series, or they use wavelet decomposition. But basically, you try to estimate how much power is being translated in a particular frequency channel. They use 70 to 200 hertz bands, because they know that this is the frequency which is related to our activity that we experience as conscious activity, in particular language related. So if you could go 10 hertz, 20 hertz, but it would be more kind of automatic body functions. But also, unfortunately, and this is very typical issue, they need to exclude multiples of 60. For the reason that electric power circuit has 60 hertz, and that noise actually shows up everywhere. And this is one of the difficulties with working with electrodes, that they hear the 60 hertz in our power outlet. Okay, so then they're basically exposing people to different words, and some words maybe are repeated throughout the experiments, but then they say, okay, so if they're repeated, let's count them only once. They end up with 110 unique words, and then each of them, GPT views each of them as a vector of length 1600. Then they say, okay, let's project the 1600 dimensional space on a 50-dimensional vectors using PCA. They need to do it because they're comparing 1600 to 81 electrodes that they have in the people. So the big deal is that they now then take this 1100 words, they chop it into 10 buckets. The buckets are non-overlapping. They do particular training on 990 words. They will estimate some parameters when they're matching AI to brain. And then for validation, they're using 110 words, which were never used in the training. So basically, you're trying to, again, find the linear transformation from GPT data to brain data. You optimize these coefficients based on 990 words. And then after these coefficients were trained and frozen, you look at the remaining 110 words. And your question is, does GPT on this additional 110 words, does GPT predict what the brain will do? And again, so they're dealing with the same issue. So this is the picture. And of course, because they try to emulate a high dimensional space on a two-dimensional situation, this picture doesn't mean that much. But at least they made it fun. So if you try to rotate the right-hand side in your mind, and the right-hand side is whatever was taken off the brain, so you will see that after kind of a linear transformation, you can rotate and flip it onto the left-hand side, which is the GPT space. Right. And so here they're speaking very conservatively in terms of geometry of embedding, in a sense, where the vectors are located, which vectors are close to each other, but they're really, when they're in the training period, when they use 990 words, it's a linear, this alignment is done by using a linear transformation. And then you say, okay, does this linear transformation work on the remaining 110 words? And let me just not not yet. Okay, so maybe I will jump, but I will need a part of this. Right, so they again comparing GPT and GLAV models. GPT uses vectors which are context dependent, and GLAV is ignoring the context. Here, the correlation coefficient, if you look, you will see it's 0.1. So this is that issue that showed up in a previous study, that you only have your useful part of the signal is just a fraction of what it is, but still you see that it's whatever the model is predicting is much more useful and has much more information than so either random predictions, or they had an alternative version where you're trying to predict based on the word that was heard, was earlier analyzed within this 990. So you choose the closest word that was used earlier. You're just ignoring what is used right now. So this is kind of a possible strategy, but it works much, much worse, right? But again, so it means that if you're looking at every particular brain cell, you can predict its activity with correlation of just 0.1. But if you have a lot of them, if you have a lot of signals, it's rather likely that you can actually predict the overall response to a word. So if you kind of bundle all of this information together across different cells, this is much more useful. Okay, so the interesting thing is that they say, okay, so when we are training AI, it's producing numbers, of course, just as soon as you're feeding a word into that. But when does the correlation start with the human brain? So you see that there is time 0 if you look at the horizontal axis. So this is the correlation is the higher. So this is when the human has been exposed to the word. But the correlation starts actually up to 700 milliseconds before. So for them, it's an indication that half a second before we hear the word, we're actually anticipating what it could possibly be. So our brain is already producing numbers which are similar to GPT numbers. We're just kind of all eager to hear, is it that? Is it that? And this doesn't happen to the GLAV side at all. So the GPT kind of correlation shows that anticipation effect much better. And so this is, again, independent confirmation that the brain is attempting to do predictive modeling. Okay, so I will need to skip all the details here. Again, basically, maybe one comment. 80% of the people will experience eventually one or another form of cognitive decline, hopefully like by later than earlier. In some cases, it will be just mild impairment of functions, and sometimes it will be dementia. If this subject is studied really well, it's conceivable that we will be able to have GPT-10 and just feed its output into living brain. So if the brain processing is not very good, for example, because we lack dopamine, maybe there is some essential function is not working, you might be able to feed the raw data from an algorithm into a brain. And so this brain region IFG that they're using, so this is whatever was available in the patients, and maybe you can find a better area. And I'm suspecting that this is why Elon Musk is doing this study with implants and everything, because for an astronaut, being able to have this raw data just uploaded to the brain, so that's a big deal. This is still very, very far, but if this study is successful, eventually, probably it's too tempting not to do that. Okay, so the last 5 minutes, a third direction. So with earlier context-free word embeddings, the word embeddings that do not rely rely on the context. They don't care what happened before. So when you convert words into vectors of maybe length 300, you observe these, what they're called analogies. And the analogies would be on a vector level, on numerical level, king minus man is approximately equal to queen minus woman. And then countries and their capitals would have similar. So France minus Paris, Poland minus Warsaw. So you would have a similar thing. So for all such things which show often enough in the text on which you are training your algorithm. So this comes up. They observe that countries and currencies don't work that well because this corpus of text you're exposing to doesn't really have enough information. So there was an attempt, how do you explain what's going on? Why this is it automatic, or does it depend on some features? And so this, I'm just listing here 4 different papers. Again, one of them is March of this year. And so all 4 of them make certain assumptions, and they all criticize other people's assumptions, but then eventually each paper still needs to make their own assumption. And so this is partially to illustrate that in 6 years of working in this direction, the question is not settled. We still don't know what are the original best assumptions to start with, and then depending on which of them are more compatible with what the brain does. So there was a conjecture stated by Pennington, Socher, and Manning in 2014 that when you talk about this verbal analogy, A is to B as X is to Y, like king, man, queen, and woman, right? So then this is supposed to be equivalent in term, so there should be a way to state that in terms of probabilities. So these are conditional probabilities. So PW vertical line A is a probability of meeting the word W if you have seen the word A, and meeting it like within a next short section of the text. Right? So if you're looking at the word A, how likely is that the word W will follow afterwards? And so they want to say, okay, for every word W in the vocabulary, you're expecting this. There is a ratio of probabilities on the left-hand side, a ratio of probabilities on the other side. And so A, again, A to B is as X to Y, right? So they kind of postulate that it should be possible to convert this existence of analogy into this numerical equality. And so all of these papers that I'm quoting, so they're all working on the AI side. You say, suppose this really happens in the text that you're feeding to the algorithm. Is it true that on a level of vectors you're getting this approximate linear equality? And let me just very briefly in one page explain what one paper is doing. So again, they're doing some training, some word embedding, and we can just look at the white formula. So this is the function that they're optimizing. They're going through all pairs of words, then the coefficient, this number CW. So they're just, so this is the number of occurrences. If you're looking at a window, just a few words, how often do these words show up there? And then in each such case, you look at all words which don't show up, and this is DCW. And then you want to optimize for the function, which is some M would be some number, but basically you're subtracting the product of vectors which correspond to words that show up together. And then you're adding a function, a product of 2 vectors, a word that showed up and the word that doesn't show up, okay? So you want to, and then the little plus function is maximum with 0. Right? So you basically want to say that if words tend to go together, then you want their scalar product to be large. If some word doesn't show up, if the word W prime doesn't show up in the same window as C, then you want this scalar product to be 0. So this is kind of their own model, but they're basically saying when you start optimizing on that function, so this will be there will be this effect that they call push-pull action. So push will be you're trying to increase the scalar products of words that show up together, and then pull, you try to decrease scalar product of words which don't show up together. And they noticed that in the older models like skip, gram, and glove, the functions which are optimized are different, but as you're optimizing it, your update steps actually do achieve this as a goal as well. So there are a lot of different functions that you could optimize that will have this side effect, that you're increasing scalar products of words that go together, you're suppressing scalar products of words which are not aligned in the same context. And so they have a theorem that, okay, so the left-hand side in that theorem, so these are just things which you can rewrite in terms of conditional probabilities. And we had that in the earlier conjecture, it was a situation when the right-hand side was equal to zeta, which is equal to 1. And they're trying to figure out what happens if it's not exactly 1, if it's approximately 1. And then they say, okay, then as a result of eventual training, you will have that the difference of vectors corresponding towards A and B will be equal to the difference of vectors corresponding to C and D, but up to this factor of zeta. And then they basically say that there are useful values for zeta, and there are, unrealistic values for zeta, which are not very good. So my questions to this are, okay, so you have 4 different ways of saying that the probability of proving that the probability equation does lead to vector level equality for the words, but subjectively that doesn't explain what is the meaning of experiencing this feeling of analogy. We have this subjective sense that, okay, so king to man relates as woman to queen. So what is going on the brain side? And given the previous 2 projects, there is a crazy conjecture that what we feel as analogy is actually the fact that numerical computation between vectors has worked out. And that's so these vector valued words are somewhere in the brain, and when we experience some kind of analogical thinking, there is some simple number crunching. And obviously, pluses and minuses are probably easier for the brain to compute than sine or cosine or a logarithm. And so basically, what our logic expresses is just a linear algebra performed in the brain. Sorry for going overboard. That's it.
Yeah, thank you so much. Do you have any questions? No. Any online questions? Okay, yeah, thank you for this amazing talk. It's really interesting. Yeah, it's especially the part about GPT-10 is feeding data to the brain directly. Yeah.
Yes.
Yeah. So
no, I think most of it will be hardware issue rather than computational.